Right, continuing back, what about limits at infinity which result in infinity? Yeah, so the notation limit x approaching infinity of fx is infinity is used to indicate that the values of fx become large as x becomes large. Similarly, you can write the following expressions: limit x approaching negative infinity, fx is positive infinity; limit x approaching positive infinity, fx is negative infinity; and limit x approaching negative infinity of fx is negative infinity. Okay, so there are four possibilities here. When x approaches positive infinity, you can hit positive infinity or negative infinity. Likewise, when x approaches negative infinity, you could approach positive infinity or negative infinity. Okay, so these are infinite limits at infinity. For example, consider limit x approaching infinity of x cubed and limit x approaching negative infinity of x cubed, the same function. When x approaches infinity, so you're trying with different values of x, 10, 10 cubed, 1000 cubed, and so on. 10 cubed is 1000, 100 cube is, you notice how many zeros? That's 1 million. 1000 cube, that's 1 billion. Billion. In fact, we can make x cubed as big as we like by requiring x to be as large as we want, right? So limit x approaching infinity of x cubed is infinity. Okay. Likewise, you can look at the negative. When x approaches negative infinity, limit of x cubed is actually negative infinity. You can see that using your graph of x cubed. So on the right, it's going up. On the left, it's going down. Okay, so when x approaches positive infinity, your value approaches positive infinity. When x approaches negative infinity, your value approaches negative infinity. I hope this is clear. You see, x cubed. So if you input any negative value for x, say negative 5, negative 5 times negative 5 times negative 5, the negative survives because there are three negatives. All right. So here are a few precise definitions. Precise definitions means these are the technical definitions of limit. They are not intuitive, they are simply technical. Technical definitions have to be stated accurately. All right. Precise definition of a limit at infinity. Let f be a function defined on some interval a to infinity. Notice a is open interval and infinity is always open because infinity is not a real number. Okay, so then limit x approaching infinity of fx equals L means that for every epsilon, you see this is a Greek letter, it's called epsilon, EPSILON, epsilon greater than 0. There is a corresponding number n such that if x is greater than n, then absolute value fx minus L is less than epsilon. What is the meaning of absolute value? It means the distance. Okay. Fx minus L means the distance of fx from L. Okay. So absolute value of fx minus L geometrically means the distance between fx and L. So distance between fx and L is less than a small number epsilon. So in other words, this says that the values of fx can be made arbitrarily close to L, okay, within a distance epsilon. Epsilon is any positive number by requiring x to be sufficiently large. That's why we say if x greater than n, then absolute value fx minus L is less than epsilon. Okay. So graphically, this means, say my function looks like this, right? In blue, you can see that it's getting closer to this particular L. Okay, but it was not always close, right? Here it's far away from L. Okay, so what is far away? That's not precise. Mathematically, you must say accurately what close means. Given any epsilon distance from L, if your x is greater than n, your graph falls within L plus epsilon, L minus epsilon. So that's the epsilon distance away from L. Okay. Precise definition, even if you don't understand, make a point of memorizing this. I will ask you to reproduce this definition. So memorize this. Okay. All right. Until next lesson.